Hey there, tech-savvy folks. Welcome to Z Tech Advisor. Today, we're diving into the fascinating world of hash functions. Buckle up because we're about to get technical. Hash functions are crucial in public key cryptography, especially for creating digital signatures and certificates. Let's break down what a hash function is, how it works, and see real-life applications to make it more relatable. What is a hash function? A hash function is a mathematical algorithm that converts any size of input into a fixed-size string of characters, which typically looks like a mix of numbers and letters. Think of it as a unique fingerprint for any piece of data. Key characteristics of hash functions. 1. One-way function. Irreversible. Once you convert data into a hash, you can't reverse the process to get the original data back. Imagine you shred a document into tiny pieces and mix them up. Even if you have the pieces, you can't easily recreate the original document. 2. Fixed-length output. No matter the size of your input, be it a single word or an entire book, the hash function will produce an output, hash, of the same length. For example, a popular hash function called SHA, 256 always gives a 256-bit, 32-byte output. 3. Unique output, collision resistance. A good hash function ensures that two different inputs won't produce the same output. This uniqueness is essential for maintaining data integrity and security. Why are hash functions important? Hash functions are used everywhere in computing and digital security. Here's why. 1. Data integrity. Hash functions help ensure that data hasn't been tampered with. For example, when you download software, a hash value is often provided so you can verify the software hasn't been altered. 2. Password storage. Websites store hashed versions of your password. When you log in, the system hashes your input and compares it to the stored hash. This way, even if the database is breached, your actual password remains secure. 3. Digital signatures. Digital signatures use hash functions to verify the authenticity and integrity of a message or document. The sender hashes the message and then encrypts the hash with their private key. The recipient can decrypt the hash with the sender's public key and compare it to a newly computed hash of the message. 4. Data structures. Hash functions are used in data structures like hash tables, which allow for efficient data retrieval. They are also critical in blockchain technology, where each block contains a hash of the previous block, ensuring the integrity of the entire chain. Real-life example, protecting data integrity. Imagine you're working for a company that needs to send sensitive documents to clients. You want to make sure the documents aren't altered during transmission. Here's how hash functions help. 1. Creating the hash. Before sending the document, you create a hash of it. Let's say the document is a contract. The hash function processes the contract and generates a unique hash value, like 2FD4A1C67822858491BB76E7391B93B12. 2. Sending the document and hash. You send the contract, and it's hashed to the client. 3. Verification by the client. When the client receives the document, they use the same hash function to generate a hash of the received document. They compare this new hash with the one you provided. If they match, the document is verified to be unchanged. If not, the document was altered during transmission. Common hash functions. 1. MD5. Message Digest 5. Created by Ron Rivest in 1991, MD5 produces a 128-bit hash value. Despite its historical significance, MD5 is no longer secure due to vulnerabilities that allow attackers to find collisions, different inputs producing the same hash. 2. SHA-1, Secure Hash Algorithm 1. Produces a 160-bit hash value. SHA-1 has also been found to be insecure against well-funded attackers. 3. SHA-2, a family of hash functions that includes SHA, 224, SHA, 256, SHA 384 and SHA 512. SHA 256, for instance, produces a 256-bit hash value and is widely used for its strong security. 4. SHA-3, chosen by NIST as a backup for SHA-2. It uses a different mathematical approach to provide even stronger security. SHA-3 can produce hashes of various lengths. 5. RIPEMD, developed by a group of Belgian researchers. It's an alternative to the SHA family. RIPEMD 160 is used in some systems, including Bitcoin transactions. Practical demonstration. Let's generate a hash using a website that computes hashes. 1. Input the message. Type "this is a message" into the hash function tool. 2. Select hash function. Choose SHA-3 with a 512-bit output. 3. View the hash. The tool will output a hash like 01B2C3D. This unique value represents the input message. 4. Small changes, big impact. If you change the message even slightly, the hash changes completely. For instance, adding a period to the end of the message will produce a totally different hash. 5. Case sensitivity. If you change a capital letter to a lowercase letter, the hash value will be entirely different. This sensitivity to small changes is what makes hash functions so powerful for ensuring data integrity. Application in digital security. Hash functions are also used in HMAC, hash-based message authentication code. Here's how it works. Esta Zenda combines the message with a secret key and generates a hash. This ensures that only someone with the key can verify the hash. 2. Receiver uses the same key to generate a hash of the received message and compares it to the sender's hash to verify authenticity and integrity. Case study: online banking security. Online banking relies heavily on hash functions to secure transactions. Here's how. 1. Transaction integrity. When you initiate a transaction, the bank system creates a hash of the transaction details. This hash is included in the transaction request sent to the bank server. 2. Server verification. The server receives the transaction request and the hash. It then hashes the transaction details on its end and compares the new hash to the one received. 3. Integrity check. If the hashes match, the server knows the transaction details weren't altered during transmission. If they don't match, the server rejects the transaction, preventing potential tampering. 4. Digital signatures. For added security, the transaction hash can be encrypted with your private key, creating a digital signature. The bank can use your public key to decrypt the hash and verify the transaction's authenticity. Conclusion: hash functions are the backbone of many security mechanisms in the digital world. They ensure data integrity, secure password storage, and play a vital role in digital signatures and certificates. By understanding and using hash functions, we can significantly enhance our digital security. In everyday life, from ensuring the integrity of your downloaded files to securing your online banking transactions, hash functions are at work behind the scenes, making sure that the data you trust remains unchanged and authentic. Thanks for joining me on this tech adventure. If you found this information useful, please give this video a thumbs up and don't forget to subscribe for more tech tips and tricks. Until next time, happy learning!